Okay, let's press on and get into Chapter 7. We are going to continue our look at integer programming. This time we are going to look at logical constraints. And we discussed this a little bit in the last chapter, so this is where we get a more full look at it. Okay, logical constraints. All right. What we can do with binary variables is use them to set a logical constraint on a model. Okay? And so what that means is that the logical constraint restricts consideration to a certain combination of variables. If we decide to do A, then certain parts of the model are in play. If we decide to do B, then certain other parts of the model are in play. Okay? And like the integer models of the last chapter, integer models with logical constraints are still developed using the standard linear programming format, and we will still use the simplex engine, which is the linear engine for solver. And we do that because linear models are the most interpretable in terms of understanding the model and in communicating the results. But actually, most importantly, the linear engine is the most powerful. It is guaranteed to find the global optimum, and so that's what we're looking for. So we want to use the linear engine whenever we can. So, logical constraints. All right. If you will hearken back to the previous chapter, we did an example of Newton Corporation, where we had 5 projects, and we needed to decide which ones to accept to maximize our net present value within a budget of $40 million. Okay, and so what you see on the screen here is the original model. Now, suppose management has decided that there is at least one project, must be international. And so projects 2 and 5 are international. So either project 2 or project 5 have to be included in the mix. And this is known as a counting constraint. Okay? So this is the additional constraint that we have to add. This is the algebraic version of it. P2 plus P5 has to be greater than or equal to 1. All right? One or the other or both of those have to be a 1. And so this becomes our new model. All right? So the expenditures part of the constraint is the same, okay, but we've added this additional constraint, P2 plus P5 greater than or equal to 1, okay? And in this case, we end up choosing both of them. And so we've still reached our budget of $40 million, but of course, our net present value, our objective, has gone down a little bit, which they always do when you add additional constraints. Well, not always. Sometimes they will remain the same, but they will never get better. Okay, so now we're going to introduce what we call an exclusivity constraint. Okay, so projects 2 and 5 require the same resources. Therefore, we can only choose one or the other. All right, so our additional constraint is now P2 plus P5 is less than or equal to 1. All right. And so we've, in the previous constraint, we said that P2 plus P5 is greater than or equal to 1. And now we are also saying P2 plus P5 is less than or equal to 1. Okay, so we need both constraints. All right. Now you might be saying, why not just make P2 plus P5 equal to 1? And of course, mathematically, you can absolutely do that. Okay. The reason that we have them both here is simply for communications purposes. All right. As you can see, the way that they are labeled at the bottom of the screen, We can see that one of the constraints is to ensure that there is an international component, and the last one is to ensure that only one or the other of them is chosen. Okay, and as I said, we could combine those last two constraints to just say P2 plus P5 equals 1, but that is not as clear as doing it this way. And of course, as you can see, our objective has again gone down because we've added another constraint. And as you can also see, our budget is no longer a binding constraint. We've constrained this so much that we're not able to eat up all of our budget. Now, let's look at a contingency constraint. Okay, so let's say that selecting project 5 requires selecting project 3. So let's say that they are tied together in some way. All right. So project 5, if we select project 5, it requires selecting project 3. So let's take a look at our possible combinations. We could choose neither one of them, and that would be consistent. We could choose project 3 and not project 5, and that would certainly also be consistent. We could try not choosing project 3, but choosing project 5. That doesn't work. That doesn't meet our criteria. Or we could choose both of them, and of course, that is also consistent. So we now need an additional constraint. P3 minus P5 is greater than or equal to 0. Okay, and so we're going to work that into our model. So here is our spreadsheet model for the contingency constraint. And so as you can see at the very bottom, this is the equivalent of our algebraic P3 minus P5 greater than or equal to 0. Okay? And as you can see, once more, our objective has gone down. All right. We chose, in this case, both P3 and P5. So now we are constraining this by budget. We are constraining this by choosing an international one. And so we've chosen P5. We have constrained it by exclusivity, so we cannot choose both P2 and P5. And we also are constraining it by contingency, meaning that if we choose P5, we must also choose P3. Okay? And so as we continue to constrain this, our objective continues to go down. Now, let's take a look at something we call the fixed cost problems. And so one of the rules of linearity is that linear programs require proportionality. So, for example, the cost of an activity is proportional to the amount of the activity. The cost of transportation, for example, is proportional to the amount that we transport. Okay. But sometimes what we encounter are fixed costs, where some portion of an activity's cost does not vary with the activity. And so technically this violates the assumptions for linearity. But binary variables allow us to accommodate the fixed cost within a linear program and still allow us to use the linear engine, and we'll show you how that works. Okay, so let's take a look at the fixed cost problem, and what we call this is the use of linking constraints, where essentially we link the fixed cost to the variable cost using binary variables. So let's say that total cost equals fixed cost plus variable cost per unit. Okay, so algebraically we'll do TC equals f of y plus v of x. All right, where f is the fixed cost and v is the variable cost per unit. All right. And so this is basically, it's a linear program, and the variable cost is the slope. Okay. So x and y are the decision variables. All right. X is continuous. All right. And y is binary. All right. One or zero. So when y equals 1 when x is greater than or equal to 0. All right? Y is 0 when x is 0. Okay? So the linking constraint is, we can express it this way: x is less than or equal to my, where m is some, it's not entirely arbitrary, but it's some large number. It's an upper bound on x. We select a number that x is never likely to grow beyond. Okay? Otherwise, the line simply keeps going up forever. All right? So we have to have a bound, especially on linear programs. We have to have an upper bound because the line just keeps going up to infinity. All right, so we have to put an upper bound on it. So let's take a look at more office products. All right, we have three departments, and they make product lines F1, 2, and 3, and there are a certain number of hours required for these products. All right. And the capacities are 2,000, 2,000, 2,000 for each of the department. Profits per unit are listed there. And we have sales costs in the thousands and demand in the thousands. And so our fixed cost or our sales costs, all right? In other words, those will not vary at all. If we decide to use product F1, F2, or F3, we will incur those costs. All right, so let's take a look at how that plays out on the spreadsheet. Okay, so let's take a look at more office products, and let's take a look at the previous problem without regard to fixed costs. All right, so our decisions are simply how much of each product line to produce. All right, and our objective is to maximize our variable profit. Okay, so we have our standard capacity and demand constraints, and in this case, demand is a ceiling. Okay, and I know we continue to struggle with that, but again, take a look at the wording of a problem, and you can usually tell whether demand is a floor or a ceiling. In this case, it's a ceiling. You want to, if it's couched in the words like a forecast, for example, that's usually a ceiling, meaning this is what we think we will sell, probably not any more than this. All right. And so this is our result. So again, this is a straight linear program, nothing to do with integers or binary or fixed cost just yet. Now, the problem with the previous solution is that the decisions are made without taking in the fixed cost into account. So it's possible that variable profit could be so low that the company would lose money. So we need to understand whether all three product families are worth keeping. All right. In other words, we have to integrate our fixed costs into the model. All right. So algebraically, we need to look at it this way. Our net profit is 1.2 times x1 minus 60 y1. Remember, 60, 200, and 100 are our sales costs. All right. So our net profit is the amount of revenue we bring in from product 1 minus the sales cost, the amount of revenue that we bring in from product 2 minus the sales costs, and so on. All right. Now, remember, our y equals 1 only if our x is greater than 0. If we decide to make a product and sell it, then y will be 1. In other words, we will incur our fixed cost. If we decide not to sell a product, make and sell a product, then y is going to be 0 and we will not incur the fixed cost. All right. Again, it takes a little bit of a while to get your head around this, but think it through, follow it through, and you'll be fine. All right. So our linking constraint is x sub j minus my sub j is less than or equal to 0. This is our linking constraint. And so m is some arbitrarily large number, something we do not expect x to go past. And in this case, since our demands are a ceiling, we could actually substitute the demand value for M here, and that could be our upper bound. So this is how it looks in the spreadsheet model. So these three represent the amount and the number of our products that we're going to sell. If and only if we decide to get into that market. So y1 is a 1, so x1 is going to be greater than 0. y2 is a 1, so x2 is going to be greater than 0. But we decide in terms of total profit that it's just not worth being in the market with the third product line. Okay? So we have a different calculation for our variable profit, our fixed cost, and then our net profit. Okay? So we're taking fixed costs into account now. And at the bottom, we have our x minus my, right? That's our linking constraint. Okay? And so these represent m. These are our upper bounds. And the reason that we chose 300, 250 are because this is a demand ceiling, so we don't expect x to ever go above these values. Okay? And as we can see, it turns out that they are all hard constraints. And that makes sense, right? Because if you are trying to maximize profit, you are going to you're going to sell as many as you think you can. All right. So our demand and linking constraints are at the bottom. Notice that X3 is just not profitable. All right. Now go back and watch this again. Try and get your head, work through the algebra, and then see how it plays out in the spreadsheet form. Okay. It's a little bit complicated, but you'll get the hang of it. Now, let's talk about another type of logical constraint, and that is the threshold level problem. Okay. Sometimes in business, we're required to participate at a certain level. So, for example, you have to buy so many of a certain product to qualify for a discount. Okay? So, the decision variable must either be 0 or the specified minimum. Okay? The objective function remains the same. So, let's let small m equal the threshold value, large M equal the maximum value like we've been looking at. And so we have two new constraints. X has got to be greater than or equal to m times y, lowercase m times y. In other words, if y is 1, then we have to participate at level m, okay, small m. But x has got to be less than or equal to y times big M. All right? So essentially, you are creating a range that x has to fall between, right? If y equals 1, in other words, if you decide to participate, if you decide to sell this product or do whatever it is that you're going to be doing, okay? So if y equals 0, x equals 0. If y equals 1, x is between the minimum and maximum values of small m and big M. So let's take a look at how this plays out in the spreadsheet. So suppose the material for family 2 of the previous example requires a minimum of 125 units produced. And that is reasonable. That's business, okay? That can happen in real life. So if we decide to make family 2, we're going to make at least 125 units, okay? So here's our model, okay? Notice that we're making 200 units of X2, of family 2, okay? So we are above that minimum. So if you look at the bottom, we have the same, this is essentially the same as the previous spreadsheet, but with one more constraint, and that is the minimum. And that is x minus small m is greater than or equal to 0. Okay, because that's what our minimum constraint looked like. Okay, does that make sense? Try again. Go back and look at it again, and you'll see how it works. Now, let's take a look at the facility location model. All right. This is an extension of the transportation model. All right. And it involves the selection of selection of the number of facilities in a network. Okay. Once the facility number and the location are decided, then it becomes basically a classic transportation model. Okay, so you remember the transportation model? You had sources, you had destinations, you had transportation costs between the sources and the destinations. All right, the facility location model just adds one more step, and that is you do not have to choose. You do not have to use all of your source facilities. You can choose to use a smaller subset of them, and we do that with logical constraints. Okay? And so this is designed to find the right balance between fixed costs and variable costs of any type of transportation network. So let's take a look at the facility location model. We call it the capacitated version. In other words, the facilities will have capacity constraints, and that's the normal type of model that we've been looking at. Okay, so the problem contains M potential facility locations and N existing customer locations, just like always. Okay, for each location, we know the capacity and the fixed costs. For each customer, we know the demand. So we're going to use binary variables to decide whether the facility will be used or not, and that the fixed costs will apply. And you're going to see that this is very much like the classic transportation model that we've been doing. So here we have Van Horn Appliance. All right. And as you can see, this looks like a transportation model. We have locations in New York, Atlanta, Chicago, and Los Angeles. And we have regions that they ship to. Okay. New York, all of these locations have a capacity and they have a fixed cost. In other words, if we decide to use New York, we're going to have a 6,000 fixed cost. All right, 5,500 for Atlanta, 5,800 for Chicago, 6,200 for Los Angeles. All right, and so the question is, which distribution centers, those are the locations, should we use to minimize our total costs? And of course, we have to stay within capacity and we have to meet demand. And in a classic transportation model like this, you know that demands are floors, not ceilings. So demand is always going to be greater than. So this is the spreadsheet model, okay, with the solution. So, for example, we will end up using, in order to minimize our cost, we will end up using New York, Atlanta, and Los Angeles. So we will have those fixed costs added to our operating costs. All right. And then after that, it is classic transportation model. On the right hand side, we have our linking constraints. That is x minus y m. Remember, large M is some kind of upper bound. And the upper bound that we're using is just the capacity constraint. Okay. So our operating costs are the sum of our fixed costs. The distribution costs are just like a classic transportation model. It's the sum product of the units times the per unit cost, and we have our linking constraints. Okay. Now there's also another way of doing this. We can make the linking constraints a little bit easier. So instead of using a separate linking constraint for each decision cell, we can do it just at the capacity level. Okay, so our linking and capacity constraints are just in one column rather than in matrix form. Otherwise, it is the same. So check out the chapter spreadsheet and you'll see that this is a little bit simpler. Okay. Now, we can also do an uncapacitated version of the facility location model. Okay. And so we can sometimes we don't know what the capacity will be, or that the capacities are determined after the location has been selected. All right. And so one way to achieve this is to run the previous model with very large capacities so that it doesn't become a limiting factor. So for example, what we've done is we've taken the capacities of the previous version, added them all together. Actually, what we've done here is we've added all of the demands together to give a large capacity of 450. Okay, so the reason we do this is when you run an uncapacitated model, it often is the case that you will only end up with one facility that's used. Okay? Remember, why do we use multiple facilities? Normally it's because we reach capacity and we have to of one facility, and we have to move on to another. But when there are no capacity constraints, it is usually the case, or often the case, not always, but often, that all of the demand will be met from a single location. Okay? And so we can run an uncapacitated version by simply putting the capacity really high. And this allows us to do like planning if we were actually going to build facilities rather than using existing ones. Now, there is an alternate uncapacitated model. It's a pure integer solution. Okay. So it says in an uncapacitated model, there is no reason to fulfill demand from more than one source. That's what I said. And so what we can do is calculate the total distribution cost per route, since all of the demand will be fulfilled from one source. All right. So it's route cost times demand. And so if a facility location is chosen, we only need to choose a route, yes or no. So the constraints become that all decisions are binary, linking constraint less than the sum of the locations, and the demand constraints greater than 1. Sometimes using the alternate version kind of freaks people out. They just got done understanding the last version, and now we introduce a new one. That's perfect. It's perfectly fine to do it either way. Okay, but if you look at it, you can see that this way makes sense. Also, if you don't want to dwell on this, I would not require you to do it one way or the other. All right. Now, let's introduce disjunctive constraints. This is where it gets pretty complex. All right. And so we want to look at what we call the machine sequencing problem. All right. A machine processes several jobs one at a time. Each job takes a certain amount of time and has a due date. All right. The job can be completed on time, which gives us a tardiness of 0, or it can be overdue, which the tardiness then is greater than 0. Tardiness cannot be less than 0. So in other words, if you finish a job an hour early, that doesn't give you a tardiness of minus something. Tardiness is only 0 or greater. So the objective is to choose the schedule that minimizes the total tardiness of the completed jobs. Now, this is actually a very complex program to solve in using the linear engine. Okay, it can be done, and I'll show you how to do it. But if you use something like the evolutionary solver, it is much, much easier. So let's take a look at Miles Manufacturing. They make metal components for the auto industry. Their jobs arrive in batches for a fabrication machine, and so the idea is to choose the optimal schedule for the jobs. There's 60 hours total of work, and the latest due date is 40 hours from now. Okay? 60 hours of work, 40-hour due date, so it is clear that not all the jobs will be done on time. All right? So we can't say that tardiness must be less than or equal to 0, right? We just have to say we need to minimize the amount of tardiness. Okay, so let's take a look at this algebraically. And again, this one is complex. You may have to go through this 3 or 4 times even to get your head around it. Okay? P is the processing time for each job. D is the due date. And let's say that S is the start time. So the job completion is the start time plus the processing time. The tardiness is the start time plus the processing time minus the due date. So for any pair of jobs, J and K, S plus P of J is less than or equal to SK, all right? Or the other way around. In other words, for any pair of jobs, J will start before K or K will start before J. All right, that makes sense, right? So Y of JK is 1 if job J comes first, 0 if not, and vice versa. And so Y of JK plus Y of KJ equals 1. One of them must come first. That means one Y will be 1, the other one will be 0. Okay? Again, go back through that, pause the recording, go back and look at this again. The algebra is not difficult, you just got a lot to get into your head. So we can express the disjunctive constraints like this. S of J and P of J, start time and processing time, less than or equal to S of K, the start time of the second job, plus the linking constraint. Okay? M times Y of KJ. And S of K and P of K less than or equal to MYJK, where M is some large non-restrictive value such as the sum of the processing times. So when job J goes first, Y of JK equals 1, and job K must start at least as late as the completion of job J. So we can do some algebraic substitution, and we are able to create the following pairs of constraints. I'm not going to read them to you, but again, work through the algebra here, stop it if you have to, okay? But you'll see that this makes sense. So we also have to track job tardiness, okay? So the tardiness of job J is T, all right? We can treat tardiness as a non-negative decision variable, all right? Tardiness of job J equals the start time of job J minus the due date, or the start time of job J, or rather S of J minus T of J less than or equal to DJ minus PJ. Now again, go back, follow the algebra through, all right? And so tardiness is always going to be non-negative. It's going to be 0 or something greater than 0. And this is how it looks in the spreadsheet model. I encourage you to open up the spreadsheet model and look at all of the formulas. You can do Control tilde to see all of the formulas. Okay. Now, as I said, this is really complex using the linear solver. And it's actually much, much easier to use the evolutionary solver, which does not demand linearity. Okay. In a lot of ways, the evolutionary solver is not as reliable as the linear solver, but for some problems like this one, it's actually superior. So now let's take a look at what we call the traveling salesperson problem. This is an example of touring constraints. So a salesman has a number of cities that they want to visit. Okay, he wants to visit each one only once with the shortest amount of distance traveled. The distance between each pair of cities is known. Okay, covering each location in a trip is known as a tour. Okay, and so we can actually use this model for lots of different applications, not necessarily related to travel. So let's take a look at the Douglas Car Company. Produces electric cars in 6 colors. The time to clean the paint machine between the pairs of colors is known. Each production run involves all 6 colors. So our objective is to schedule the sequence of painting to minimize the amount of cleaning time. Okay, and so notice that that the cleaning time is not necessarily symmetrical. Okay, so the cleaning time between pairs of colors is not the same in both directions, and that's perfectly fine. All right, so the solver will pick the optimal sequence. So this is how we set it up. we start with a random schedule: 1, 2, 3, 4, 5, 6, 1. Back around to 1. Okay. Notice that on the left-hand side, we simply have our data, and what we've done in the blank cells is added a very large number. Okay. In other words, we're discouraging the solver from using that cell. All right. Because 1 to 1 or 2 to 2 doesn't have any meaning to us. So we just put a big number in there. All right. And so our decision matrix looks exactly like our cost matrix. Okay. So in a lot of ways, this is like a transportation problem. It's actually like the assignment model. Okay. And the sums, both vertical and horizontal, are going to equal 1. Okay. Just like the assignment problem, and the objective is a sum product of the decision variables times the cost variables. Okay. And so the question is this optimal? Now, this was picked at random. Okay. So it is unlikely that it is optimal. Okay. So this is what we begin to do. We run solver. All right. And remember, that was not the what we saw on the last slide was not what solver gave us. We just put those numbers in randomly. So after we run solver, we get an objective of 120. All right. And we're like, wow, that's way better. Okay. But there's a problem. Okay. So let's take a look at, let's start with 1. 1, just follow me here. 1 goes to 5. All right. Let's drop down to 5. 5 goes back to 1. Okay. All right. So that doesn't work for us. Okay. 2 goes to 3. And then 3 goes back to 2. Okay. So we end up with what are known as subtours. 151, 232, 464. And this often happens without some additional constraints. The only constraints that we have had so far are that each horizontal row has to equal 1, and each vertical column has to equal 1. Okay? So we've got to add additional constraints to eliminate subtours. So for example, if we want to eliminate 464, we can add the following constraint. The cell that contains 46 plus the cell that contains 64 is less than or equal to 1. In other words, it can't be both. It can be 1 or it can be 0, but it can't be 2. Okay? And so we can only choose that route in one direction. So when we eliminate, we add one additional constraint, and so we eliminate that subtour, and we run it again, and we end up with 2 subtours. Okay? So let's eliminate the 232 subtour. All right? And we run it again, and again we end up with a couple of different subtours. Okay? So we have to limit to eliminate 4, 5, 6 subtour. We have to limit any combination of 4, 5, and 6 to at most 2 links. 3 locations, 2 links. Okay? So we will do it again. Okay? We will say that x of 4, 5 plus 4, 6 plus 5, 4 plus 5, 6 plus 6, 4 plus 6, 5 is less than or equal to 2. Okay? It gets a little bit tedious, but we have to eliminate these subtours in order to come up with an optimal solution. All right? And so here is our solution. Okay? Our objective is 147.5. We've eliminated all of our subtours. Okay? But what's the problem? Well, as you can see, we have 0.5 in our decision variables. Okay, so we obviously need to set these variable cells to binary. Okay, and so we add the binary constraint. We start getting subtours again. All right, we eliminate 151. And here we are at our final solution. Okay? 1246531. That is our optimal tour. Or notice we come all the way back around to 1. Okay? And our objective is 167. Okay? So it's a little bit tedious, it's a little bit redundant, but it's actually not difficult. Okay? You've just got to eliminate subtours. And you can try and eliminate them all at once. All right. Some people don't do it one. They won't eliminate one and then run it again and then eliminate another. So some people will eliminate them all with constraints. Okay. It really depends on the size of your model. But this can be handy. This actually has a lot of different applications. Okay. And as we see, not necessarily related to travel. Go back over and look through these problems again. All right. And so I want to make sure that you understand them, that they make sense to you. So, in summary, okay, if we introduce binary logical constraints, we can see that it makes a variety of optimization models available to us, including extensions on linear programming models that we've already seen. Okay, some large models can take a great deal of time. All right, and so in that case, it may be necessary to increase the integer optimality parameter to improve solver's response time. It gives you a little less than optimum result, but it may shorten the time. Okay, and that is it for this chapter, and we will pick it up again in chapter 8.